we have talked about buffers and we derived the equation for Henderson-Hasselbalch. So now let's see this in motion. So I'm telling you that we have a buffer and how that buffer was prepared. Prepared it with, say, 30 mils of 0.15 molar acetic acid and 70 mils of 0.2 molar sodium acetate. And I've given you a pKa here. And I want to know, first of all, do you think that the pH of the solution is going to be above or below the pKa? So I look at this and I'm thinking, okay, my 0.15 molar and only 30 mils of that, and that's the acid, and 70 mils of 0.2 molar sodium acetate. So my inclination is going to be that it's going to be greater than, but I want to do some math real quick to figure out, because it's going to be whichever one has the larger amount of moles is going to dominate this solution. So the way we need to do that is first convert everything into moles. So what do I have? 0.15 moles of my acetic acid, OOH, in 1,000 milliliters of solution. And then I have 70 milliliters of 0.20 moles of NaCH3COO minus per 1,000 milliliters. So what do I have? 30 divided by 123 times 0.15. So this gives me 0.0045 moles of acetic acid, COH, and divided by 123 times 0.2, 0.014. So I'm predicting then that because I have more of my conjugate base, that I'm going to have a pH that's above the pKa. That's just kind of like my quick check. There shouldn't be a minus there if I included the sodium. Come on. CH3COO minus. All right, so now let's apply our Henderson-Hasselbalch. What I know is that these are going to be my initial amount of moles. Now you can think about this in terms of the concentration, or I can be like, I'm going to have, let's see, for my base, my weak base, my weak acid, I'm going to have, let's see, 0.014 moles divided by 1,000 milliliters. I'm sorry, divided by 100 milliliters. Because that is the total volume of the solution. And then I'd have this divided by my acid. My weak acid is 0.0045 moles divided by 100 mils. What's going to happen? My 100 mils is going to cancel out. The quantities flip in my division and volume goes away. So the takeaway for this is that I can convert it to molarity if I wanted to, because then I'd have to do that and then convert my mils to liters and then do the division. Either way, my volume is going to cancel. So you're not doing anything wrong. You're going to get the exact same answer. You're just adding in an additional step if you do that last conversion. So let's see, what's our pH then? Our pH is our pKa. Let's see, I've been given pKa, so I don't need to convert my pH or my Ka to a pKa. It's going to be 4.77 plus the log of my two concentrations. So I have my weak base. I'm just going to write this as base over acid. Weak base is 0.014 divided by 0.0045. And what do I get here? see, this gives me 0.492915 is what this calculation comes out to. See how many sig figs of that I hold on to. Let's see, I have 2 sig figs in both of my calculations for moles. There's 3 sig figs here and 2 here and 3 here and 2 here. So that means I'm going to have 2. So I'm going to go 2 after the decimal. And this is 2 after the decimal for addition, subtraction. So my final answer is going to have 2 after the decimal. And I get 5.26. 5.26. So that's how that looks when we apply it straight away. So what we want to do is make sure that we convert things to moles for what we are actually working with. Don't just grab on to the molarities, because if I'm only using a portion of that 1,000 mils, then I'm not going to get a correct answer, right? Because if I use my molarity, my straight up molarity for each of the initial concentrations, I'd end up with more than I think I have of both. Make sure that you do that step. Now let's look at this. I'm going to combine 20 mils of HCl with 80 mils of ammonia. And first I want to know, is this a buffer? So what do you think? I'm thinking it is. I'm thinking it is indeed a buffer. And how do I know that? Well, I'm going to add together a strong acid plus this weak base. And what do we say about strong acids? That they completely dissociate, right? So what's going to happen is every one of my HCl, so long as I have enough ammonia in there, is going to donate a proton to my ammonia. So I'm going to end up with NH4+. So that is a one-way arrow because I have a strong acid. And then my buffer solution is actually going to be this NH4 plus H2O, yielding in both directions, liquid aqueous, my ammonia. And I could write that and water. It doesn't matter. So what have I done? I'm sorry, plus H3O. Oof, pay attention. I'm donating a hydrogen plus H3O plus. Cool. And I look at this. This gives me my Ka, or is an acid reaction, so I'm going to use my Ka, so that's fine. I have my acid and my weak acid and my conjugate base. Let's label those. So here's my weak acid, and here's my conjugate base. But I've given you the molarity of HCl and the molarity of ammonia. We haven't done anything yet to figure out what the initial concentrations are for my buffer. Because remember, I need to be in this stage of the game in order to use the Henderson-Hasselbalch. So what I can do is write things out in terms of my initial acid reaction. HCl aqueous plus ammonia aqueous going to ammonium. And if you want, what we can do, so you're not panicking about balancing, is I can write it as H+. Right? Now I can see that it is balanced. I could have written it with H3O+, and what would that have given me? That would have given me ammonium plus water. So I'd explicitly be writing water in there. All right, so what do we know? I know that I have this 20 milliliters, write it over here, 20 milliliters of 0.15 moles of HCl over 1,000 milliliters. Oops, 1,000. That'll give me my moles of HCl. And then the other one, what do I have? I have 80 milliliters of 0.20 moles of NH3 plus divided by 1,000 milliliters. And that'll give me my moles of my ammonia. If I put that in my calculator, what do I get? I don't know. It's a number. There we go. Trying to cheat and use what was already saved in my calculator. Can't find it, so I'm just going to go ahead and do it. 20 divided by 3 is 0.15. This gives me 0.0030 moles of HCl. And 80 divided by 1,000 times 0.2 gives me 0.016. So I'm starting off with 0.016 moles of this and 0.003 moles of my acid. Now, it's a strong acid, and I have less of it than I do my ammonia, so I'm going to use all of this. And I'm starting off with 0. That'll go to 0. Let's see what's happening with my ammonia. I am reacting it with that acid, so minus this 0.003 from the acid. What's going to happen here, I'm going to add that 0.003. They're all 1-to-1 ratios. If they're all 1-to-1, then I can see how that's going to change. So the 0.016 minus the 0.03. 6 minus the 0.003 gives me 0.013 moles of my ammonia. And I don't even need to put that in my calculator. I don't know why I picked it up. 0.003 moles of my ammonium. So now think about this. Which one is which? Which one is my weak acid and which one is my weak base? Well, my ammonia is accepting the proton. That's my weak base. And my ammonium can donate a proton. It is my weak acid. So remember, the other way to look at this Henderson-Hasselbalch is that this is my weak base divided by my weak acid. Do I have a pKa? No, I have a Ka. So I need to remind myself that the Henderson-Hasselbalch equation then is going to be pH equals the negative log of my Ka. 5.8 times 10 to the negative 10. And then plus, remember we can use moles. We could combine the solution values and turn them into molarities. But again, the volume is going to cancel out because they're both the same. So plus the log of my moles. So weak base, where's my weak base? 0.013. I don't know why I put parentheses there, that's okay. Divided by my weak acid is my 0.003. Let's see, from the last problem that we did, well, I don't think I actually went into it in detail there. One of the things we can look at is that if I have more moles of my weak base than I have of my acid, I would expect this to be higher, my pH to be higher than my pKa. If the reverse were true, if I had more of my weak acid than my weak base, I would expect my pH to be lower than. Another way of thinking that is just the addition. I have more acid than I do base, so I would have a lower pH. If I have more base than acid, then the reverse is true. So let's see, catalog 5.8 times 10 to the negative 10. So what do I get for this one? I get like 9.2366 plus 0.013 divided by 0.003. 0.63682. So let's talk sig figs. All right. For my molarities, I had 2 sig figs. And my molarities went into giving me my moles. And you'll notice I did something here. I left off the 0 here, make life easier. One of the mistakes that I see students make a lot is they do that and they assume that they only have one sig fig. I did that. I made that one sig fig. The problem did not. So I need to be careful when I do things like that. And my KA had 2 sig figs, so 2 after the decimal here and 2 after the decimal here. Now I can add those values up. That means I'm going to have 2 after the decimal. Addition, subtraction is the fewest after the decimal. This plus this, I get a pH of 9.87. And I'm done. So these look intimidating. They're actually a little less math than we've been doing to solve these problems. So hopefully you will find them a little bit more palatable, I suppose. Some of the things to keep in mind is defining what is initial. So if I am preparing a buffer, the initial is going to be whatever I've mixed it with. So I mixed it with this acid to make the buffer to get my weak base and its conjugate. And it's, well, you can think of it either way. I have a weak acid and its conjugate base, or the weak base and the conjugate acid. This equation here doesn't care what side of the equation they live on. So if you decided to flip it, you haven't done anything wrong. It's just, it is what it is, and you'll end up with the exact same thing. It becomes important, though, then to be able to identify which one is your acid and which one is your base. So who's my proton donor and who's my acceptor. If you label them, then it doesn't matter, again, which direction you write your equation. You're going to have the correct quantities. But we can take the strong acid or the base needed to generate the buffer and write that reaction out with a single arrow, because that is going one way. I'm going to use all of my acids. So long as I have that mole ratio present, the strong acid or base is going to go away. We get our initial concentrations or initial mole amounts, and that is what we can use to determine the pH of our buffer. So this buffer is going to be pretty basic, but remember what the buffer's purpose is, if I need something that stays pretty basic, is that it resists change, right? So now I'm going to give it something, if I add more acid, it's going to react with the weak base and lower the pH some, but not by much. All right, so Wednesday we will do another example with this and make sure that you're nice and comfortable, and then introduce this concept of titration curves. It's going to be fun.